Okay, we're going to briefly look at time evolution of a single spin system. But first, I want to say that we'll give more of this later, but we'd prefer to do this in the rotating frame. And like I said, I'll give a separate lecture on this later. But for now, all we have to know is that the frequencies we're going to be using will be the Larmor frequency minus, the rotating frame frequency. So this is basically, if you take an axis system, z is the direction of our field, we're going to rotate it around that at the Larmor frequency, so that now we're in a sense only looking at things relative frequency away from the central Larmor frequency. So you're only looking at chemical shift differences, etc. So where, of course, generally our frequency holds is the gyromagnetic ratio times the magnetic field it's in. Okay, so with that in mind, we'd like to look at time evolution, which we've avoided so far. So far we've looked at quantum mechanics, in a time-independent way. And now we would like to look at the time-dependent Schrodinger equation, right? Most commonly written, it's a function of both spatial and time components. The Hamiltonian, where we put the time dependence in the wave function. For our purposes, we'll write it as the time dependence here minus I h. Minus I. We'll put the h into the Hamiltonian and write it in a kind of a more simplified term like this. Okay, and what wave function are we using? Well, this is looking at it in terms of our wave function here, right? We've said we would generally write that as a superposition in the following term. So that's the most general form of a one-spin. I is equal to 1/2 wave function. So okay, so with that in mind, we're going to take the derivative as the function of time of this wave function, where now these coefficients are time dependent. And now, as I've said here, we'll more generally write our Hamiltonian where we would normally write it like this. Now we're going to write it using a rotating frame relative frequency. So it's basically the same thing. It's a frequency. It's just only the difference in frequency. So minus I, this frequency, the IZ operator, and then our wave function, which is superposition of beta. And I've left out, but these are time dependent. Okay. So now just going through this, CA, which is time dependent. CB, which is time dependent. Minus I, our frequency. So now IZ, it's time dependent, but the IZ operator, it's still just, constant. So IZ operates though on eigenfunction alpha, and well, this is time dependent, it still doesn't operate on the IZ. IZ doesn't operate on it. This is beta, and we know this term, which is minus a half beta, and we know this term, which is plus a half alpha. Right. So that simplifies it a little. However, at this point, to further simplify this, we're going to basically do a trick where we multiply by a complex conjugate. And you could do this of either alpha or beta. So we'll just say that we're going to multiply by, we'll do alpha. But and again, you can do the same thing for beta. So what is that doing? That is just putting an alpha here, an alpha here. Right? I'm just going to multiply through the whole thing, an alpha here. And let me see if I can move this a little and make room. An alpha there. Right? So we multiplied everything through by the complex conjugate of alpha, the wave function. Okay, so this goes through, right? So now we can say it's the derivative of C alpha T alpha alpha. So you can already see why this is starting to be important, because we know that this basis set, these eigenfunction, they're orthonormal to each other. So alpha alpha and alpha beta have specific meanings here. Again, it goes through this. We know what that is. So it'll be minus a half I frequency C alpha, which is time dependent, which is the constant. Again, that goes through that constant, alpha alpha, and then plus 1/2 I C beta, and then this is alpha beta, right? So that's equal to 0, it's equal to 1, it's equal to 0, it's equal to 1. Right? So that has greatly simplified things. Now the derivative C alpha T with respect to time, that constant is time dependent, is minus a half this frequency C alpha. And this, the solution to this is very well known in differential equations. So I'm just going to write it here, and we can prove it in a different screencast. It'll be C alpha at time 0, the exponential of minus a half I frequency T. Okay, now again, you could do the same thing up above, but multiply by the complex conjugate of beta, and you would see that you would get the beta term here. It's time dependence, which will be the same thing as above, set plus, right? And so the solution will look similar to, it'll be C beta times 0 e to the I omega t over 2, so the plus. Okay, now we'll start to, in the next screencast, we'll start to use that and show what its implications are. Thank you.